Okay, so welcome back. In today's lecture, we're taking a slight detour away from algorithms to talk about a notion called big O notation. And the reason why we're doing this is because next time we're going to look at algorithms and formalize a way of describing their time complexity. So we have to measure the complexity of an algorithm somehow. And the way that we're going to do that is with the use of this notation. Okay. So I have to warn you though, that the way that I'm going to describe it is as it's described in Rosen. Okay. I'm actually not that big of a fan of the way the Zybook describes it. It works, but I think that Rosen has a better description of it, and it's more formal to me. That's probably because Kenneth Rosen is a mathematician, and the people that wrote the Zybooks are CS professors. Just different conventions for things. I prefer Rosen. Okay, so there's a definition that's going to kind of guide the entire section. All right, so definition. It's going to take me a second to write. So let F and G be functions from either the set of integers or the set of reals to the set of reals, or some like subset of the reals. Okay. So we say that f of x is big O g of x. So this is red, big O. So big O g of x. If there are constants, capital C and lowercase k, such that in magnitude, so the absolute value of f of x is at most c times the absolute value of g of x whenever x is greater than k. Okay. So this is an inequality. And it's my experience with math majors, CS majors, regardless of like what year they are, that inequalities they seem unnatural to you. Like you're so used to working with equations in your math courses that inequalities might seem a little bit off. But realistically, inequalities are more common in real world scenarios. Like most things are too complex to get an actual equation for, at least like with relation to data. So the best that we can do is bound things. So this is a bound, right? So that less than or equal to that's a bound on this thing's value, right? So what this is saying is that, so if f of x is big O of g of x, then like in magnitude, as x is increasing, right? At some point, so there's like a cutoff k, right? At some point, for all x greater than that cutoff, the magnitude of f is no more than a constant times the magnitude of g. If there's some cutoff where they're no different than a constant multiple. Okay? Which, if they're no different than some like constant multiple of each other, right? Like this one's no more than that, right? Then like we have a way of like saying like this one we have a way of describing this one's behavior in terms of this one. That's the whole point of the idea. So let's look at an example. And we'll do several examples. So show f of x equals to x squared plus 2x plus 1 is big O of x squared. Now, before I work through actually showing that that satisfies the definition here, I like to encourage my students to kind of look at it and think for a moment about what happens as x gets really big. So imagine x is like huge. Like, let's just say not even that big at first. Like, let's just say like x is like 1,000,000. It's not that big of a number, right? It's just 1,000,000. There's much bigger numbers, but let's imagine that x is 1,000,000, right? This thing here, right? Like, does that one really matter when x is 1,000,000? No, right? So like, I'm gonna erase this in a moment, but like, x squared plus 2x plus 1 is like approximately x squared plus 2x, right? When x is really big, right? But even then, like if x is like 2 to the power 1,000,000, that's like way more atoms than there are in the universe, right? Huge number. That number squared is going to be so much larger than 2 times that number, right? It's essentially the same thing. So then if x is like really, really big, then it more or less behaves like that function.
So if x are really, really small,
It can behave any kind of way when x is small. But as x goes really large, that's where we want to know, like, it's almost like considering what we call like the asymptotic behavior of the function. As the inputs get large, what is it behaving like? Right? So even before like proving that that is big O of x squared, I already have an idea that when x is large, these kind of behave roughly the same. So it would make sense that maybe I could bound that one from above by some constant multiple of that at some cutoff point, right? And the cutoff point is that k. Like for all x greater than that k, they're gonna be bounded in this way, hopefully. Okay. So before, well, no, I don't have to write it yet. We can do this one without what I was thinking. So let's look at the solution to this. So before we wrote the solution, we kind of gave ourselves an intuition as to the behavior of that in relation to the other one. So now we're going to try to show that there are indeed constants like this. Right? And if we can show the existence, right, the existence of C and K such that this holds, we're good. So let's just look at like, okay, the absolute value of x squared plus 2x plus 1. Okay. Now, it helps to like drop the absolute values, right? Like when kind of manipulating sums and stuff. So I'm just going to note that this is like equal to x squared plus 2x plus 1 when x is greater than or equal to 0. I can just drop the absolute values, right? In fact, when like that part's like greater than -1, it's going to be positive, right? When we drop the absolute values. But this for sure makes we can drop the absolute values, right? So then I have to think about like, okay, my goal is to get to like some constant multiple of x squared, right? So next observe that this is at most x squared plus 2x squared plus x squared when x is greater than or equal to 1. Why is that? Because x squared is greater than or equal to x when x is greater than or equal to 1, right? And if x is greater than or equal to 1, then x squared is also greater than or equal to that one right there. So like that and that, so that's greater than or equal to that. And then that is greater than or equal to that. It's important that x is greater than or equal to 1 though, because if x is in the interval 0, 1, then the square is less than x. Like think about like 1/2 squared is 1/4, it gets smaller. But if it's greater than or equal to 1, then I know that's greater than or equal to that, that's greater than that. Okay? So then I just have like terms, I can combine them. Right? So this is going to be equal to 4x squared. And again, I'm keeping track of my condition on x. Okay. So now this is the same thing as writing that. So then we can do this. Take c to be equal to 4 and little k equal to 1. That function is at most 4 times the absolute value of this function whenever x is greater than or equal to 1. So basically what's happening here is it like this thing gets bounded above by a constant multiple of x squared kind of quickly. Like right after x is greater than or equal to 1, 4 times x squared is going to be greater than or equal to that function. So it's just a way of it's a way of giving a measurement on the growth rate of this thing, this function. Now with relation to algorithms, how would this relate? You can, given pseudocode, you can measure the number of atomic or basic operations that need to occur. Like how many times that you're adding something, how many times you're checking a Boolean statement. You can count the number of operations in an algorithm and write it as a function. It'll probably be a messy function. But then you want to kind of give a measurement to that function. It's big O of some simple function. So it's like a way of measuring how complex your algorithm is. So that's where we're going. Okay. So let's look at another example. So show 7x squared is big O of x cubed. Now this one is almost easier in a sense, because as soon as x is greater than or equal to 7, this is going to be at most x times x squared, which is x cubed, right? So this one is kind of easier. We should still write out the formal solution. Okay. So just look at the absolute value. That this is equal to 7x squared. That's always positive in there. We don't have any conditions on x, it's just positive, right? But then this is at most x times x squared. This is another way of writing right over there. Whenever x is greater than or equal to 7. This is equal to x cubed. And I'm just like, you don't really have to do this. I just like to keep track about this business here on each line personally. And then finally, this is equal to the absolute value of x cubed. Again, x is greater than equal to 7. So we found our c and our k. C is 1, k is 7. These are called the witnesses to the big O instance. So then you would just like write this explicitly out. Take capital C to be 1, and lowercase k to be 7. Done.
No.
Okay. Now, let's look at a case where we show that a function is not big O of another one. So show n squared is not big O of n. Now, surely, like this one would make like immediate sense that that's not big O of n, right? Like, there's no constant that's going to like save this, like from like not falling behind that, right? Because this is like n times n, any constant times n. As soon as n is larger than that constant, then that's going to be bigger, right? And that actually points to like how you would show this. You would assume by contradiction that it is big O, and then get a fallacy. So if you're going to show something is not big O of another function, then the way to do this is with contradiction pretty much every single time. Okay. So by way of contradiction, suppose n squared is big O of n. Okay. Now, nice thing about contradiction is that under this assumption, we get all this information. We get that there's witnesses to that big O instance. So if that is big O of n, then there exists capital C, lowercase k, such as this. So then, by definition, we'll just write it out. I'll abbreviate definition for the sake of board space. So then by definition, there are constants. Capital C and lowercase k, such that the absolute value of n squared is at most C times the absolute value of n when n is greater than or equal to k. Okay. So this is for any n greater than or equal to k, right? Any n. So eventually, like n is going to be positive, right? At some point, n has to be positive, which means we can drop the absolute values. So this means so when n is greater than or equal to k and n greater than 0, equal to 0, whatever. Okay. And then since n is positive, right, we can divide both sides of that inequality by n, and the inequality doesn't change direction or anything. So we get that n is at most c. And again, when n is greater than or equal to k, and n is greater than or equal to 0. So for any n that satisfies this, that's going to be true. What's wrong with that statement right there?
What's the question?
What's wrong with this last line here? Something's wrong. There's a problem. So n is going to keep on getting bigger, and what? And c is going to stay the same. C is a constant, right? That's going to fail whenever, because this has to hold for every single n greater than or equal to this k, right? Forever. But c is a constant. So since c is a constant, we can just write that out, like, since c is a constant, and n goes to infinity, we have a contradiction. And it is a proof. So assuming the opposite of this leads to a contradiction, so the original statement must be true. Okay. Any questions about that? Like, you could have done it directly now that I'm thinking about it, but I think contradiction also is just easier, maybe. All right, so there are some important theorems and like big O results on like these like base functions, like polynomials, logs, exponentials, things like that. And that's what we're going to kind of derive next. We're going to start with a theorem. It's a general theorem about polynomials. So, theorem. So, f of x equals to a subscript n times x to the power n plus a subscript n minus 1 times x to the power n minus 1 plus plus a1 times x plus a0 is big O of x to the power n. So hopefully you recognize this notation here. This is a polynomial. So all those a's are real numbers. An is non-zero. It's a polynomial. So basically, this is saying that if you have a polynomial of degree n, then that function is big O of x to the power n, which is kind of related back to like what we said earlier, right? Like when x is huge, right? When x is like 2 to the power a trillion, like this means nothing compared to that. It means absolutely nothing, and that's what's like dominating that term. Okay. Now to write out the solution to this, we need a lemma. And a lemma is derived from a Latin word that roughly translates to a tool. It's like a proposition or a theorem that is used as a tool when proving other things. And it's called the triangle inequality. Okay. So, have any of you ever heard of triangle inequality? So it basically states, in its most basic form, it says this, that the absolute value of A plus B is at most the absolute value of A plus the absolute value of B. So the absolute value of the sum is at most the sum of the absolute values. And that's like the most commonly used form. But this extends to any number of things. So like the general version is this. So x1 plus x2 plus dot 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 plus xn in absolute value is at most absolute value of x1 plus absolute value of x2 plus dot 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 plus absolute value of xn. That's the general version. When n is 2, it's like the same thing, right? So the absolute value of the sum is at most the sum of the absolute values for any real numbers. Okay, and we're going to use that over here. So proof of. So I'm going to start by looking at the absolute value of this polynomial. Dot, dot, dot. Big O absolute value. Okay. And then we're going to immediately apply the generalized triangle inequality. We have the absolute value of the sum is at most the sum of the absolute values. All right, so absolute value of an times x to the power n plus absolute value of an minus 1 times x to the power n minus 1 plus dot 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 plus the absolute value of a1 times x plus the absolute value of a naught. And that's by the triangle inequality. Okay. Now, so this is like an inequality. A property of absolute values is this as well. Absolute value of a times b is equal to the absolute value of a times the absolute value of b. That's just a property of inequality of the absolute values. So notice we have like a bunch of like products here, so we can rewrite that. So absolute value of a n. And I'm going to drop the absolute values on the x, because I'm just going to assume that x is greater than or equal to 0. So I can just drop all of those out, right? I have to keep the absolute values with the coefficients, though, because I don't know if those are positive or negative. So this is when x is greater than or equal to 0. I can drop the absolute values on all those x's. Okay, so next up, we need to somehow write this as a product of x to the power n. Okay. So if x is greater than or equal to 1, that's at most x to the power n. That's at most x to the power n. And there's a 1 multiplying that, right? There's a 1 multiplying this a naught thing. So if x is greater than or equal to 1, x to the power n is greater than or equal to that 1. So this is at most absolute value of an times x to the power n plus absolute value of an minus 1 times x to the power n plus dot 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 plus absolute value of a1 times x to the power n plus absolute value of a naught times x to the power n. And that's when x is greater than or equal to 1. So like That's greater than that, that's greater than that one, that's greater than that, so forth and so on, right? Provided x is greater than or equal to 1. Okay, so next, I'd say like, let A equal to the max of the set absolute value of an, comma, absolute value of an minus 1, comma, dot, 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 absolute value of a naught. So whenever there's a finite number of things, you can find the maximum. And there is a finite number of things, right? There's n plus 1 of them. So A is just going to be the maximum of all those. So this here is at most A times x to the power n plus A times x to the power n plus dot, 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 plus A times x to the power n plus A times x to the power n. I'm not writing the condition on when because I'm going to have to fit stuff this way now. But you see that, right? Like A is the largest of all the coefficients in magnitude, so this is definitely greater than or equal to this. How many of those do we have? These terms? N plus 1 of them, right? So this will be equal to n plus 1 times A times x to the power n. Again, we're just like making bigger and bigger estimates, but now we have that, right? And if we wanted to, just to be clear, we could write this as c times absolute value of x to the power n when x is greater than or equal to 1, and c is equal to n plus 1 times a. And then there it is. That's a constant. N is a constant. Like n is a finite number. A is a number. It's a number, so it's a constant. So what did we just show? Ran out of boardroom, but like this is at most constant times that whenever that. Thus, that polynomial is big O of x to the power n. So c is equal to that, and lowercase k is equal to 1. Those are your witnesses. And then it's not like the best looking proof, but that's the idea behind it. Use the triangle inequality, take the maximum of the absolute values of coefficients, combine like terms, and then you have that polynomial is no more than that. Okay. It actually like tells you like what the constant is as well, right? Like if any polynomial you have, like you take the max and absolute value of all the coefficients, and then times that with the degree plus 1, that's your c. And then your lowercase k is just 1 always. So no matter how complicated that looks, it's no more than just that number times x to the power n. Okay. So now we have a theorem that we can use whenever we encounter a polynomial. We know immediately the big O estimate for it. Okay, more examples. I'll get a new black marker. That one's even worse. Let's see. show 1 plus 2 plus dot 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 plus n is actually, instead of show, let's do this without like a target to do. So find a big O estimate for f of n equals to 1 plus 2 plus dot 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 plus n. So find a big O estimate now, not just like show it, but find it. Okay. So for this, it's actually not so bad. Oh, and whenever you see n, like it's typically going to be an integer, a valued function, or a natural number valued function, or input function, I mean. So like n is clearly just positive in an integer. So if you look at the absolute value, 1 plus 2 plus dot 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 plus n, that's clearly equal to 1 plus 2 plus dot 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 plus n. This is just positive, right? But then 1's less than or equal to 2, or strictly less than 2, right? And 2 is strictly less than the next one. They're all strictly less than n, right? So then I can write that this is strictly less than n plus dot 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 plus n. How many n do we have? N of them, right? So this is equal to n times n, right? Oh, wait a minute. Is it the case? I saw one of you wince. How many of them are there? There's just like terms. There's n of them. Yeah, there's n n's. So it is n n's, right? Like if there was 3 n's, it'd be 3 times n, right? But we know there's n of them. There's n times n. N squared. So then this function here, the f of n is big O of n squared. That's it. And like that type of thing, like could definitely occur in an algorithm, right? Where like for each loop you do, like you increment one operation, right? And there's like n loops and you're incrementing n at a time. So like this could like measure the number of operations in an algorithm. And we'll define that formally next time. Okay. Let's look at another example. Show n factorial is big O of n to the power n. Now, if you ever have an algorithm that the number of simple operations is any type of factorial, it's probably a horrible algorithm. All right, solution. Factorial is n times n minus 1 times n minus 2 all the way down to 1, right? So well, it's always positive, by the way, so we drop the absolute values. Yeah. That's just the definition of the factorial. Now, notice that what's the largest factor here? 10. right? So that's greater than or equal to that. It's also greater than or equal to everything following it, right? So this is at most n times n times n times dot 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 times n times n. Right, this is it. So you're multiplying n times, so it's going to be n to the power n. And that's obviously equal to the absolute value of n to the power n. 2. Okay. So in particular, what we just established really, like in general, like that's the solution right there. But like we've also established here that, in fact, like, yeah, n factorial is at most n to the power n, right? That's what we just established for like all n, right? There's no conditions on it, it's just that, right? So make note n factorial is at most n to the power of n implies that log of n factorial is at most log n to the power n. Why is that true? It's only, you can only apply functions on both sides of an inequality when certain things happen. The logarithmic function is increasing, right? So it's increasing, so if we apply on both sides, right, and that's less than that, then log of that is less than or equal to log of that. So it's increasing. Which this implies that log of n factorial is at most n times log n, which implies that log n factorial is big O of n log n. So we have like another, we've established another result. Okay. So this is a big O estimate on log n factorial. And in many instances, when you're measuring growth of algorithms, you're measuring those atomic operations, there is logarithmic growth. It's not like super fast, it's like kind of bendy, right? So that's why it's important to have like log estimates on things. And speaking of, I'll just state a fact that, what do I want to say? I want to say, oh, it's like that's true. I'm just telling you that that's true. We'll prove it later in the semester, but that's true for all positive n. And if you wanted to like verify it with like calculus or something, you could also do that. We're going to prove it with something called induction later. But with calculus, you can already see it as well. Like just take n to be x and x is positive, right? And then just evaluate like, okay, put x to be like 1, right? So then 1 is less than or equal to 2, good. And then look at the rate of change, take the derivative. On the left-hand side, you have a constant rate of change, and on the right-hand side, you have a growing rate of change. So that one's always going to be greater than the other one. But using this, we can determine that log base 2 of n is at most n. If you take the log base 2 on both sides, 2 to the power n collapses to n, and then you have that. So, but really, like, this implies a little bit more because if we recall from like a pre-calc class, log base b of n is equal to log n, oh, so that's like natural log, by the way, log n over log b. Okay, log n over log b. So what this is saying is that this is less than n over log b. And if you don't see like what's happening, what I'm trying to emphasize here, that this is 1 over log b times n. That's a constant. It's a constant. So, and what this means is that log base b of n is big O of n for any base b. I wonder if the camera can pick up my ankle popping. It's like pretty loud. Okay. And on that note, because my ankle is killing me right now, I think that'll be it for today. And we'll finish this off next time and then start talking about using it to measure algorithms. All right, I'll stop the recording there.